Hello, my name is Will Rand. Welcome to my SPH3U ISU video. Today, I'll be exploring the relationship between the mass of an RC car and its acceleration. This is the car I'll be using for today's demonstration. When I took it apart, I realized that it had dual 36-volt motors supplying 14 watts each. For this project, I ran 5 tests, adding different amounts of weight to the Silverlit Exhaust 360 car and measuring how fast it finished on a 3-meter track. Here is a chart reflecting the data that I gathered. To calculate acceleration, I used the formula A equals 2d over t squared, where d is the distance, 3 meters, and t is the time it took to finish the track. Here is a graph of this data showing a downward inverse curve. The power-to-weight ratio compares the power output of a motor to the car's mass. The formula for power-to-weight ratio is P over M, where P is the motor power and M is the total mass. My car has two 14-watt motors, so total power would equal 28 watts. Here I have calculated the net force of each trial in newtons. And here I have the power-to-weight ratio for each trial as well. As expected, runs with a higher power-to-weight ratios accelerate faster. When the car is heavier, the ratio drops and the acceleration slows down. So why exactly does the heavier car accelerate slower? It comes down to Newton's second law, which states that F equals ma. This means that acceleration of an object depends on two things: how much force is applied and how much mass the object has. In my case, the motors always apply the same amount of force, but as I add mass, the car's acceleration has to go down. The force is being spread over more weight. So with each extra load, in this case, a battery, the car takes longer to speed up. This is exactly what the law predicts. Now let's look at a couple real-world examples. So a Tesla Model 3 Performance makes about 500 horsepower, which is around 373,000 watts, and weighs roughly 1,850 kilograms. That gives it a power-to-weight ratio of about 201 watts per kilogram. That's why its 0 to 100 kilometers speed is just 3.3 seconds. Compare that to something like a Toyota Corolla, which has about 138 horsepower, translating to about 103,000 watts of power. Its power-to-weight ratio is only 79 watts per kilogram. That's less than half of the Tesla's, and it takes around 8 seconds to hit 100 kilometers per hour. You can clearly see the same trend in my RC car tests. At 0.486 kilograms, my car had a power-to-weight ratio of about 57.6 watts per kilogram at the start, and it accelerated the fastest. By the time I had loaded it with 1.03 kilograms, the ratio dropped to 27.2 watts per kilogram, and the acceleration cut almost in half. So, in both small-scale tests and real cars, more weight equals slower acceleration, unless you boost the power to keep up. That's Newton's second law in action. This is exactly why cars like a Bugatti Chiron have higher acceleration, even though it weighs 2,000 kilograms, can still accelerate very fast, because it has 1,500 horsepower to make up for the weight. Its power-to-weight ratio is so high that drag and mass become less of a limitation. In conclusion, this experiment demonstrates that adding weight lowers power-to-weight ratio, reducing acceleration. This matches Newton's second law and physics of force and motion. Thank you for watching.